Next one is variance. The variance is not very useful. How come? Well, because, for example, if we are talking about distance, and the distance is measured in miles, let's say. When we talk about the variance will be measured in miles squared. What does that mean? Right? If we're talking about the distance, I mean, the standard deviation will always be the same, will always have the same measurement unit with the observations. Here, if I talk about distance, this is in miles. So sigma in miles, S in miles. So the standard deviation for the sample and the population standard deviation, they will be in the same measurement unit with every observation that I have in the data set. But here, variance is denoted by sigma squared, and of course, S squared, depending on population and sample. But the measurement will be miles squared. You could say, but that's area. Right, but I cannot compare it to the measurement, to the observations. It does not have the same measurement unit. What will that be? Exactly the same thing, but squared. So without the square root. So sigma squared will be just the sum from xi minus mu squared divided by n. And of course, this one will be the same thing, the sum of xi minus x bar squared divided by n minus 1. Okay, so these are the main measures of dispersion. However, we have two more. One is called it's used only for bell-shaped. Empirical rule for bell-shaped distributions only. Okay, what is the empirical rule? What's the deal with this? Okay, so I have a graph for you, and I'm going to add this in. If it's not clear, I will create my own. Is it visible? If it's not, I will write it again with my own writing.
It's visible, but I can hardly make out the numbers.
Yeah, the writing's too small.
Okay, very good. No worries. It's a very simple situation to graph. Okay, so this is a bell-shaped distribution, as we see. So the empirical rule says that approximately 68% of the observations, so it could be either mu for the population or x bar, doesn't matter. It works for both. So, and these will be mu plus 1 sigma, of course it's minus over there, mu plus 1 sigma and mu minus 1 sigma. So again, what does this mean? It means that if the distribution is bell-shaped, it is expected approximately 68% of all the observations to be within 1 standard deviation away from the mean. And of course, it can be x bar minus s and x bar plus s. Same thing, just different notation. Okay, that's step one. Step 2. Approximately 95% of the observations, if it's a bell-shaped distribution, will be found between these two observations, approximately, with mu minus 2 sigma and mu plus 2 sigma. Of course, the same notation with x bar minus 2s and x bar plus 2s. So 68, 95. And the last one is 99.7. Approximately all 99.7% will be within 3 standard deviations. So mu minus 3 sigma or x bar minus 3s, same thing. And right here, this point is mu plus 3 sigma or x bar plus 3s. So 68%, 95%, and 99.7%. This is the empirical rule.
Do you not get the full 100%?
It's approximate. We can have what is called outliers. So we still can have something here or maybe something here. So that's an approximate.
Okay.
Yes. If it is bell-shaped, nothing is 100% bell-shaped or perfectly bell-shaped. There is one other rule, and this is the last one before we can start working on different examples, which is called, it was a Russian mathematician who came up with this, Chebyshev. Chebyshev's inequality. So remember, the empirical rule is for bell-shaped distributions. Don't forget, for bell-shaped. You cannot use this. You cannot use this concept if the distribution is not bell-shaped. He was so interested in all this, and he came up with the idea that for any, and this is very powerful, any distribution, he said, for any bell-shaped or otherwise, we will find, so we know, you know how we, from the empirical rule, we said plus or minus, right? Same thing here. We have mu plus or minus k sigma. Okay, for any distribution, what is k? K is a number greater than 1. He said that 1 minus 1 over k squared times 100% times 100% of observations will lie within k from the mean. We can determine this once we establish k. If we have k, we just plug it in the formula. So for example, if you say if k is 1.2, all I have to do is just calculate 1 minus 1 over 1.2 squared, multiply by 100, and I will tell you that mu plus or minus 1.2 sigma will have such and such percent of observations. That's what it means. So once you tell me k, and you say find the percentage of observations within 1.2 sigma standard deviation away from the mean, then all I have to do is just plug in 1.2 and I will tell you what is the percentage, approximate percentage within 1.2 sigma away from the mean. If you say now calculate with k equals 2, fine. I will put 1 minus 1 over 4, calculate that, which is 75%, and I'll tell you 75%. So if you want me to repeat this procedure for any, but I have to have the data set, I have to have, and of course this is the same thing for x bar plus or minus ks, of course, all of them. So I have to have the data set, I have to have the mean, I have to have the standard deviation. And once I do, you can ask me for any k, and I will be able to calculate the approximate percentage of observations in that data set that will be found between mu minus 1.2 sigma and mu plus 1.2 sigma. Just let me establish this just to make sure. This is an interval like this one. When we say mu minus sigma, mu plus sigma, we're saying this interval, right? When we say the same thing. So when we are told mu plus or minus 1.2 sigma, it means the minimum is mu minus 1.2 sigma, and the maximum here in this interval, mu plus 1.2 sigma. So this has to be understood as an interval at all times. I have one more data set for you.
I have a question about
Yes,
this.
any question, yes.
Did you say that this was only for bell-shaped, or was this for any distribution?
For any.
Okay.
This is for any. He said, of course, it's all approximate. It's not 100%. You don't expect to get an exact, correct 100%, but it's a very quick way of determining where the data lie within the mean, away from the mean. So the empirical rule is specifically for bell-shaped distributions, but Chebyshev's inequality works for anything. I have one more data set for you to enter so we can take a look at and answer some questions. So I want, what am I doing? Where is my, what happened here? Aha, good. Okay, so I did enter the observations already. I already created my data set. It's about cholesterol level for 54 female. This will be easier to enter and faster. So please go to StatCrunch and click on New Data Table. New. Don't forget to save. So whatever we did, so always go to Data and save again. It will say overwrite. Yes, yes, I want to overwrite. Make sure you save results, graphs, and settings. Make sure you overwrite existing file and save. When that is done, so let's go to New Data Table. Although these are 54, it will go much faster, no decimal numbers. Let me know when you're ready to enter the data set.
Were you naming any of the variables?
Oh, yes. Let me see. Let me show you how I did it on this. Very good. Thank you. Yes. I labeled it the whole thing. I said HDL for 54 females. And in the column, I only said HDL. And I entitled it, but it's up to you. You can use your own style. You write whatever you want. And I called it HDL. So let me know when you're ready for the first column. And don't forget to save.
Ready.
Okay? Okay, very good. I'm going to start the recording. I'm going to stop the